All right, so this is the review for the second worksheet for your test 2. So first thing that you need to do is label the parts of this atom, so matching up these letters to the correct answers. So see if you can figure out what those are. Go ahead and predict, and then we'll check it. Okay, so then here are our correct answers. Our protons are these that have the plus sign. Our neutrons have no sign on them because they don't have a charge. The electrons have the negative sign. The nucleus is this whole chunk here in the middle. And then the electron energy levels are the rings that are going around the nucleus. And remember, electron shells and electron energy levels refer to the exact same thing. Okay, so now talking about parts of an atom, we're going to talk about the atomic number, atomic mass, also known as the mass number, and then finally the net charge. Okay, so we know the atomic number, that is your number of protons, and what you need to know about that is that as you add protons to an atom, that changes the actual identity of the atom. It changes what element it is. So if we add a proton, we go from hydrogen to helium, then we go up to lithium, and then it keeps going like that. Which is like what we did with the Build an Atom simulation, where you guys drug in the protons, and you can see that that name of the element changes each time. Okay. All right. So then next, excuse me. Here we go. So here, this is the parts, the mass, atomic mass, or mass number, meaning the same thing. That is always going to be not the protons plus the electrons, the protons plus the neutrons, So as we add more neutrons, we're increasing the mass of our atom, but we are not having any effect on the actual identity. So if we look at that mass number, right now we're at boron, atomic number 5. It has a mass of 5. As we add neutrons, that is increasing the mass, but we still have boron. Okay, and it also is not affecting the charge at all. We have 5 protons, so we have a plus 5 charge. Neutrons are neutral. They don't affect that charge at all. What does affect the charge is the number of protons and electrons. So if we've got the same number of protons as we do electrons, then we're going to have a net charge of 0. If we start adding in some electrons here, right now we have 5 protons but no electrons, so we have 5 unbalanced plus signs, a charge of plus 5. As we start adding in electrons, now that net charge is going down because those negatives are canceling out the protons. And then if we keep adding, after we get to a net charge of 0 or a neutral atom, keep adding electrons, now you can see the charge is becoming negative because the electrons outweigh the protons. Okay, next, let's talk about actually reading the periodic table. So these questions down here. We're going to talk about the groups, the periods, the families, and average atomic mass, and how that is different from just atomic mass. All right, so first, the group number is what tells you the number of valence electrons an element has, so that's your first question. Okay, so remember when we did these Lewis dot diagrams, the dots just represent the number of valence electrons that an element has, and that matches up to its A group number. Now this is only for the A groups. So when it says for which elements does this work, it's just the A group elements. So groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So that is skipping over these transition elements. So when it says which elements are not included in this group, in these groups, we're talking about the transition elements, which does also include the lanthanides and actinides. These down here, these are part of the transition metals. So it's all the transition metals, including lanthanides and actinides, that rule does not apply to. Okay. Next. So now we're talking about the electron shells, or the electron energy levels that an atom has, and that is equal to the row number. Okay, so you can see in period 1, we have just one shell, one circle. Period 2, there's going to be 2 circles. Here, this is showing how lithium loses an electron, and when it does, we erased that outer shell, and so now it has an outer shell that looks just like helium, but that's only after it loses that outside electron. It starts out with 1 valence electron. And then in period 3, we have 3 shells, and as we keep going down up to 7 shells, the period number, the row number, tells you how many shells it has. Let's see, and another name for electron shells, that's electron energy levels. So that should answer those last 2 questions on the bottom here. Next is the families, and let's take a look at this one next, because that's at the bottom of your worksheet, sorry. Okay, I want you to know, when you're reading a symbol, that smaller number that's going to usually be like right above the letter or in the corner, that's going to be your atomic number. And I want you to know that N, that represents the symbol. It's either going to be the first 1 or 2 letters of the name, and it could be a different funky name, like for gold, aurum is the name. Then you have the actual element chemical name, and then the average atomic mass. And that average atomic mass is different from the regular mass. So just the atomic mass, that's protons plus neutrons, but the average is a little bit different. And so let me show you what that's about. Average atomic mass, and we don't have a spot to, oh wait, we do have a spot to write that down. It's on your next page. I'm doing things just ever so slightly out of order. So on this next page, underneath that periodic table, we have what's the difference between average mass, or average atomic mass, and atomic mass. And so in your average atomic mass, that's going to be the decimal under this. It is the average of all of the different isotopes of that atom. So for example, this is in nature, there's 2 types of chlorine, 2 isotopes of chlorine. There's chlorine 35 and there's chlorine 37. And most of the chlorine in nature is made up of the 35. You can see that that's over 75%. And then the 37, that's only about a quarter of the chlorine that exists in nature. And so that's why the average is in between, why it's 35.45. So I can actually show you, this is the another simulation, like the Build an Atom simulation, and you can look at some of those different mixes. In hydrogen, there's 99.9885% of the hydrogen is this type, hydrogen 1, that has no neutrons in it. Hydrogen 2 makes up it makes up like a 100th of that hydrogen in the entire world. So yeah, it's very, very uncommon. And some of them have, different amounts of mixture. Here's beryllium. Beryllium doesn't even have any isotopes. It's all just one thing. Neon has a couple of different mixes, a couple of different isotopes. Here's helium. There's the one helium-3, the rest of it's helium-4. Argon, there's a couple. There's one helium-38 and then a few 36s. So depending on what element it is, it might have more isotopes. It might not have any isotopes, like phosphorus has none. So the average is the average mass of all of the isotopes. And that is different from the atomic mass, which is just for a particular atom, how many protons and neutrons does it have added together. Okay. Let's go back then to families. So that's above this particular question right up here. I want you guys to label where the families are on here. So if it helps, here's some labels as well, but I want you guys to know where those different elements are. You can use your periodic table on your test, so please make sure that you have a copy of that available. You must have your periodic table with you when you take your test. Okay, down at the bottom of this page, I have some element properties for you. Okay, so which groups are very reactive? That would be the alkali metals and the halogens. So that's group 1A and 7A. And so looking here, that's this group and this group. And then the next question that you have on this chart here is, why are they so reactive? Well, if we remember the octet rule and we remember how many valence electrons these have, the alkali metals have only one valence electron, and then the halogens have 7. They need to have 8 or none. And so the halogens, they just need to get one more electron, so they're really, really eager to get it. They have a very, very high electron affinity. And then the alkali metals, they want very much to get rid of that one electron because they could be stable if they just get rid of the one. So they have a very low electron affinity. They want to get away from it. And so because the alkali metals just have to get rid of one and the halogens just have to gain one electron, that is what makes them so very reactive, because they're just so close to being stable, to fulfilling the octet rule. Okay, the next one is, why are the noble gases, group 8A, almost not reactive at all? Well, remember, the group number tells us how many valence electrons that element has. And so all of the elements over here in the noble gases in group 8A, they all have 8 valence electrons. They've already satisfied the octet rule. They don't need to react. They're done. They're happy. They're stable. So they're not going to react unless you put them under a whole lot of pressure. So their reactivity is almost none because they will react if they're under enough pressure, but it doesn't happen in nature. It can only happen in a laboratory. Next we have the metals are on the left side, non-metals are on the right. So when you look at that periodic table, all of these things are metals except for hydrogen. Hydrogen is a non-metal. So all the rest of this stuff, 75% of the elements on the periodic table are metals, and then just a few of these guys over here, the nonmetals, the halogens, and the noble gases are all technically nonmetals. All of these are. These just have also some special characteristics, which is why they get an extra name. There's just these guys who are the little nonmetals who aren't in one of those special groups. Okay. Metals are conductive, and nonmetals are insulators. And so my question for you is, why are metals conductive and nonmetals insulators? Well, like we said before, these guys over here, the alkali metals, they just want to get rid of one electron. They want to pass it along. So do the alkaline earth metals, but instead of one, they want to get rid of their group number, which is 2. They want to get rid of 2 electrons. And these guys, they want to get rid of 3 electrons. These guys also want to get rid of electrons, but they're not quite as concerned about it. But these guys, all of the metals are going to be conductive because they want to get rid of electrons, and getting rid of electrons and letting electrons move along is what allows things to be conductive. Nonmetals, they want to hold on to electrons, so they're going to keep electrons from moving, which is what makes them insulators. Okay, so next we have that metals form cations. Obviously, they get rid of electrons, so then they have more protons than electrons. They have a positive charge. They're cations, positive cat. And then nonmetals form anions. They are gaining electrons. Then they have more electrons than protons, so they are negative. The electrons outweigh the protons. And then we have the elements in the same family. They'll have similar chemical and physical properties. So same types of chemical reactions that occur, but also similar properties like their color or state of matter, solid, liquid, gas, those kinds of things, how soft they are, how hard they are, those sorts of physical properties, but also chemical properties, how they react with other substances. Both of those things are true. Okay, that's it for this part. And now we're on to the last